and improves our resilience against various threats, such as algorithm-driven attempts to guide our behavior, personally tailored fake news, viral powers of social media, and massive data-intensive analysis of our movements. What is more, computational thinking has irrevocably changed the tools, methods, and epistemology of science. Learning CT has many benefits beyond programming. If you try to understand what computational thinking is from media accounts, you will hear a story of problem-solving with algorithms, along with the ability to think at the many levels of abstraction needed to solve problems. The story is flavored with images of joyous children having fun programming and playing games in which they simulate algorithms. Indeed, our teachers have learned much about computational thinking from teaching computing to children, and they have developed superb ways of teaching fundamental computing insights to newcomers. In this book, we call this CT for beginners. But the K-12 education insights and debates barely scratch the surface of computational thinking. At the more advanced levels, computational thinking concerns the design of hardware, networks, storage systems, operating systems, and the cloud. Its historical predecessors have organized human teams to do large computations, organize production lines in manufacturing, guided lawmakers, and specify the rules of bureaucracies. It has developed styles attuned to major areas where computing plays a critical role, such as artificial intelligence, large data analytics, software engineering, and computational science. We will show you all this by examining the kinds of computational thinking needed to deal with these different dimensions of computing. A much more advanced kind of computational thinking is needed to deal with these areas. We call it CT for professionals. Computational thinking is sometimes portrayed as a universal approach to problem solving. Take a few programming courses, the story in the popular media goes, and you will be able to solve problems in any field. Would that this were true. Your ability to solve a problem for someone depends on your understanding of their context in which the problem exists. For instance, you cannot build simulations of aircraft in flight without understanding fluid dynamics. You cannot program searches through genome databases without understanding the biology of the genome and the methods of collecting the data. Computational thinking is powerful, but not universal. Computational thinking illuminates a fundamental difference in the ways that humans and machines process information. Machines can process information at billions or trillions of calculations per second, whereas humans do well at 1 calculation per second. Machines process with no understanding of the data they are processing, whereas humans do and can correct errors on the fly. Machines can transform a mistake into an algorithm into a costly disaster before any human has a chance to react. Thinkers in the philosophy of mind, neuropsychology, cognitive science, and artificial intelligence have studied these differences and shown us how fundamentally dissimilar they are. Although some human tasks, like searching and sorting, can be eased by applying algorithms to them, most computational thinking in the big picture is concerned with machine computation. Think for a moment about the speed issue. A typical computer can, in 1 second, perform 1 billion calculations and draw a complex image on the screen. A human would need 100 years to carry out the same steps at human speed. Humans obviously draw pictures much faster than that, but machine designers have yet to imitate that human capacity. If humans had no help from computers, we would have no real-time graphics. Nearly everything we see software doing is made possible by the incredible speeds of computers. These machines, not humans executing algorithms on their own, are the reason for the computer revolution. Computing machines do the humanly impossible.